Welcome back, nerdlings. There we go, I got it right that time. Sweet. Cool. Today we are doing section 1.4-ish. And I have to say ish like that because when you go to do your homework, out of the honors textbook, this is not a mistake. On the calendar, it does say go back to page 103 to do 3 questions. That's not an accident. It's because I'm following the order of the AP book, okay? And the AP book takes material from an older section and moves it into section 1.4. But we don't have those books yet. So just so you know, on the calendar, that's not a typo. It does say page 107, okay? Anyway, building functions from functions. I like to call these function operations or algebra with functions, arithmetic with functions, I should say. In order to be successful with this, you need to be able to understand function notation. This is function notation. This is what it's telling you to do. The mistake that I see most often from students when they see something like f plus g of x is they will add functions f and g together and then they'll multiply by x because they think this means times x. This does not mean times x. This means of x. It means you're going to get a new function. X is still the variable. That's what that means. Okay. So for the sum, f plus g of x, you add f of x and g of x. And nice thing about addition is that order doesn't matter. 2 plus 5 is the same as 5 plus 2. So order doesn't matter. Life is easy. It's usually just going to be you combining like terms. The difference, f minus g of x, once again, that does not mean times x. It means function f minus function g is done exactly the same way. You just make sure that if it's polynomial in nature, when you subtract, you distribute the -1. But something that you also have to watch out for is order. Order matters. 2 minus 5 is not 5 minus 2. Order matters. So g minus f is g of x minus f of x. Just watch out for order. Product fg of x. Again, this doesn't mean times x. It means function f times function g. F of x times g of x. And 2 times 5 is the same as 5 times 2. So once again, order doesn't matter. Just watch out for it. Because for division, order does matter. 5 over 2 is not 2 over 5. Order matters. So if I say f over g of x, you do f of x divided by g of x, and you just make darn sure that the bottom function can't equal 0. So division will often introduce new domain restrictions that you didn't have before. Not always, but often. And, like I said, order matters. So g over f of x is a different equation. This time, f of x can't be equal to 0. What we're going to be doing when we perform these operations is getting a new function and then figuring out what is its domain. Because it says in each case, the domain of the new function consists of all the numbers that belong to both the domain of f and the domain of g. Unless it does things like that. So it's really like this. When you build a new function out of other functions, you just make sure your domain didn't get larger. That's all that happens. Domains could be exactly the same, or they could get smaller, but they'll never get bigger. Okay? Cool with that idea? So for this example, f of x, the squaring function, if you recall back to what they called it in Friday's notes, has a domain of all real numbers. So the only thing I would ever have to watch out for is making sure that this didn't end up on the bottom of a function, and if it did, then x can't be equal to 0. But anything else I feel like doing with it, add, subtract, multiply, whatever, any number you want to use. But that, square roots have restrictions. We've talked about them several times already. We cannot take the square root of negative numbers. So what we have to do is we have to make sure that x plus 1 is never negative, meaning greater than or equal to 0. If you subtract 1 from both sides, what we find is that we need x to be greater than or equal to negative 1 for g of x. So that's for g of x. For f of x, x can be any number it wants to be. Let's do some math. Let's find f plus g of x. We take f of x and we add g of x. Ta-da. That's it. You can't do anything else. They're not like terms. So we now have a new function. In order to find its domain, we look for structures that have restrictions. Oh, look, it's that same square root bar. Its restrictions have not changed. So the domain of this new function is that. But I'm going to write it in interval notation. There we go. That is the domain of f plus g of x. It's pretty easy, right? Subtraction. F of x minus g of x. Done. They're not like terms. You can't do anything here. All we need to do now is identify the domain. And the only part of our function that has a restriction is that square root bar. That square root bar has not been altered, so the domain has not been altered. Boom. Last of the boring ones, fg of x. That means f of x times g of x. Done. There's nothing else you can do. But we can identify the domain. And the only part of this function that has a restriction is that same square root bar that still has not been altered in any way. Questions, comments, concerns so far? Easy, right? Let's do one of the fun ones. Order matters. This says f over g. Function f over function g. And our domain has been altered. Does anybody know how? What's different now? Adi?
It can't be -1 equals 0.
X can no longer equal -1. Good job. Because if x was -1, I would have the square root of 0 as the bottom of my fraction. My domain got smaller. You good with that, Jack? You looked like you were deep in thought about it. Okay. You know, I know it's not part of the notes, and period 2 didn't see it, but I'm going to go ahead and do g over f to talk about its domain. Because it's interesting. The square root bar tells us that we can only use numbers from -1 to positive infinity. But the bottom of this fraction says, well, you can use anything you want, except for the number 0. We have a problem there, though, because 0 was part of this one's domain. So what happens? The domain says begin at -1 and then go all the way up to 0. But you can't include it. But you can use any number bigger than that. It's got a really interesting domain. You see, order of the fraction matters. Not only would it give you a different function, it'll completely change the domain a lot of the time. Isn't that cool? I mean, I think it's cool. I'm a huge nerd. I think it's really neat. And how about GG? Got any gamers in the room? GG. I used to make that my test password sometimes. Kids would be like, what's a password? I'd be like, GG. It means good game. But when you say it sarcastically, though, or like when you lose, you'd be like, oh, GG. So, yeah. Yep. Anyway, let's do function g times function g. What is that? It's just x plus 1, right? Okay. Now, what you're going to do is you're going to think about what the domain is. Just get it in your mind, what the domain is. You got it in your mind? What you think it is? Okay. Oh, you can't see what's on in the video. They can't see the screen. Yes, I'll do it on the calculator. Yep. Look at you. I'm going to expect a lot out of you on this first test.
Please don't.
You better not disappoint me.
You know what? I'm used to disappointing people. I think I can just that was really set.
Zoom 6. It's almost as if this graph doesn't exist to the left of -1. It's because, no, it's undefined to the left of -1. How are you going to take the square root of a negative number? I told you, the domains cannot get larger. The domain of this is -1 to infinity. The domain of this is -1 to infinity. So the domain of this is -1 to infinity. Again, the domains cannot get larger. Regardless of what you did, you have knowledge that this is the original equation. All domains are determined before you do any algebra. Domains are always determined before you do algebra, okay? Now, if I just said, hey, what's the domain of this straight line? Obviously, the answer is all real numbers. But you have knowledge of the fact that that was not a straight line. It was actually a square root times a square root. And those have restrictions. Restrictions cannot be removed. Cool with that? Yep. It's even more impressive on Desmos, but this isn't a screen recorder. It's recording what the camera sees. So, what? But if I do it on, well, I mean, the only reason why it's neat on Desmos is because I can press this little button and it pops up. No, this image is upside down if I show it up at the computer screen. Like right now, it's recording my hand on these notes that you don't see because it's recording the camera, not the screen. But anyway. Okay. So I was doing that. That'll be in the video, me running my hand under the camera. Compositions are even more fun. And by fun, I mean nerd fun. Fun from me. Compositions are literally you building an equation by plugging one equation into another one. So we're going to, instead of plugging numbers into equations, we're going to plug equations into equations. You guys, I'm a lot older than you, but you've probably never seen the show, but you've at least seen the Pimp My Ride memes. You ever seen the Pimp My Ride meme? No? She's seen one. Okay, well, I'm going to get through the video, and then if there's time, I'm going to find a Pimp My Ride meme and show you why it's funny. Because mathematically, it works. Hey, I heard that you like functions, so I put functions in your functions. And now you can function while you function. You'll see. Anyway, so we're going to build equations. We're going to build new functions by literally plugging one into the other. So this could be shown either as f of g, fog x, or f of g of x, and that is an O. It is not a dot. That does not mean multiply. It means of. I prefer this notation, but you will see both. And because of that, I purposely did this example with the little O. Order matters. Okay? Domains cannot get larger. They can stay the same, or they can become more restrictive, but they can never become larger. I'm going to say that f of x is the blue one. And I'll say that g of x is the red one. F of x is a quadratic. And if you recall to Friday's notes, the domain of all quadratics is all real numbers. G of x is the square root function. Its domain is from 0 to infinity, including 0. Let's see what happens when we plug things into other things. A, I don't like the O symbol, so instead of writing GOF, I'm going to write, wrong color, G of f of x. And this is color-coded. So the red stuff will be this, and the blue stuff will be this. The way I've written it, they're going to put the blue stuff into the red stuff. The red stuff was square root of. Now, normally I told you when you substitute to please do it with parentheses, right? Okay, that's why I'm going to put parentheses in here, just to show you that I always follow my own advice. But are those parentheses serving a purpose? No, they do absolutely nothing. If it had said square root of 2x, well, then they would have done something because you would have had to distribute the 2. But there's nothing going on in there, so when I write this new equation, I'll drop them. I hope you're not writing large. I meant to warn you ahead of time, don't write large. I'm sorry. We need to find the domain of this new function. And this is a quadratic underneath a square root bar, like you saw on the extra credit. It's almost like I keep bringing it up for a reason. Almost like I plan on putting it on a test. He said with his eyebrows up really high. We find the domain of quadratics underneath radicals using a sign diagram. Because you cannot take the square root of a negative number, we have to make sure that this x squared minus 1 can only give us positive values, or 0, because you could take the square root of 0. This factors. That's what it factors to. It has two zeros, positive 1 and negative 1. You put those two numbers on a sign diagram, which is just fancy speak for a number line that's been split into zones. Those two numbers split my number line into 3 zones. 1, 2, 3, count them. Okay. What we have to do is test the zones to find out if they're going to be positive or negative. Because remember, I can't take the square root of negative things. There's no math to show. It's all done mentally. So hopefully you're mentally checked in. Because you won't be able to say, well, I wrote it down in the notes, unless you write all the things I'm about to say. You take a number to the left in -1, like -2. It doesn't matter. You just take a representative. What we're going to do is we're going to plug -2 in to either here in the factored thing or here in the unfactored thing. It doesn't matter. Because all we care about is whether or not it's going to be positive or negative. That's all we care about. I suggest you do it here for future mathematics purposes. So -2 plus 1 is negative. -2 minus 1 is negative. And when you multiply two negatives, you're going to get a positive. That is a zone that my quadratic is allowed to exist in, because I could take the square root of all of those positive numbers that would come out of there. A representative between these two numbers is 0. I love the number 0. It plugs in so easily, because 0 plus 1 is positive and 0 minus 1 is negative. The product of a positive and a negative will be negative every single time, and I cannot use the negative values of that quadratic. So I cannot use any of the x's between -1 and +1. And then you grab a representative out here, like 2. 2 plus 1 is positive. 2 minus 1 is positive. 2 positives multiply to give you a positive. Your domain is where the positive values would exist. From -infinity to -1 included, union, 1 to infinity, including the 1. If this radical, square root of x squared minus 1, had been on the bottom of a fraction, I would not have been able to put brackets on the 1 and the -1, because that's where the radical has a square root of 0. So it wouldn't be allowed to exist on the bottom of a fraction. On the top, it's fine, though. And the last thing, what we were actually supposed to do is figure out what is g of f of 4. That's what we were supposed to do. And that just means plug a 4 into that thing. So you put a 4 right here. 4 squared is 16. 16 minus 1 is 15. That's the easy part. The real part, the actual knowledge, was the domain of the composition. I love doing domains of compositions because I love mixing things up. I like putting radicals and fractions, fractions and radicals, fractions and fractions, radicals and fractions, and all of those things put together. Fractions and radicals inside of fractions. And then asking my students to find the domain, because it's neat. B. I might need space. Necesito espacio. Okay, part B. This is f of g of x. So I take the blue function, and everywhere I had an x, I have a set of parentheses. And I will be throwing g of x into that set of parentheses. Together, red and blue make purple. What? That's red and blue. That's red and blue.
That is absolutely red. You want to get your eyes checked.
No,
The button looks red to me. That was
the button is red.
the button is red. I don't think
Yes.
it's red though.
I don't know. Anyway, what's the new equation? What's the equation? X minus 1. But the real question is, what is its domain? What is its domain? What's the domain of the red thing? Oh, well, 0 or positive. So guess what? That's this one's domain. The domain of this comes from its parents. The domain cannot get larger. Since the red domain is x is greater than or equal to 0, which would be 0 to infinity inclusive, that's this one's domain also. Once again, it's half of the line. And then we're supposed to do f of g of 4. So it's just going to be 4 minus 1. Once again, the neat thing is the domain of the composed function. Not bad, right? Not too scary? No, it's, I mean, like, I can make them bad.
Oh, okay, then we're good.
But the skills wouldn't change.
No, that's fine.
Yep.
Remember doing this?
Square roots, whatever's underneath the square root, greater than or equal to 0. Whatever's on the bottom of a fraction can't be equal to 0. So you put a square root on the bottom of a fraction. Now it's just strictly greater than 0, because you can't include the 0 anymore. But if I could take two functions and build one out of them, I should be able to take one function and take it apart and get back the constituent pieces. This is called decomposition, taking the functions apart. What I'm telling you is that h of x is something with another thing plugged into it. Our job is to take it apart. I think the easiest way to do this is to say what was plugged in. So on part A, what looks like got plugged in? X plus 1. Sure does look like x plus 1 got plugged into two places. Remember, that means it would have replaced x's of the original function. So then our f of x is just x squared minus 3x plus 4. And you're finished. It is that easy. That's it. Part B. For part B, there are a lot of correct answers, a lot of correct ways of doing it. But there's two very easy ones. I would like for someone to tell me the easiest they could think of and to tell me what got plugged in. Charlie.
F of x could just be x, and g of x to be square root of x cubed plus 1.
Oh, she took it really, really easy. She cheated. You're not wrong. That actually works. Okay, I'm gonna write it down. She cheated. Okay, here's what she said. She said f of x could have just been x, and then said that g of x was the square root of x cubed plus 1. She's absolutely right. That technically that works. That's okay. Okay, that's not what I was hoping for though. So let's what looks like got plugged into something else. Okay, Mark. That's what I was hoping to hear, but yeah. And that would make the f of x square root of x. There you go. Yeah. I was hoping that you would go for that one.
To be fair, I had both of those down.
Yeah. Oh, did you really? So you were just being extra on purpose. I see you. But no, you're right though. That works. It's actually a trick that we use in mathematics in section 1.5. It's actually a trick that we use. remind me, if you would, to bring that up. And okay. And if you really wanted to be extra, you could have said, I'm just listing lots of other ways. You could have said that g of x was just x cubed, and that f of x was the square root of x plus 1. And it goes on and on and on and on. I mean, I could add 1 to this and subtract 1 from this and keep doing that, and I would have other correct answers. But I'll go ahead and tell you that there is a question like this on my test. There is a decomposition question on your test. You would have known that eventually anyway because it's going to be on your review. My suggestion for you would be to watch out for distributions. Yes, Mark? I don't remember. I think there's 15. Yes, on computers. Yep. Alrighty. What I tell you guys, it was the Friday is the first day of review. It's a 3-day weekend, so Tuesday would be the second day of review. So the test would be Wednesday of next week. Yes. Hold on. Everybody, nope, nobody panic. Mark, is this a question about the hurricane? Okay, what's up? On paper review, and you'll have it in class for 2 days, and we can work on it and stuff together. Mm-hmm. If we miss a day from the hurricane, clearly I'm going to have to back everything up by 1 day. It would be terrible. Okay, modeling with function composition. In the medical procedure angioplasty, doctors insert a catheter into a heart vein and inflate a small spherical balloon on the tip of the catheter. The reason why they do this is because they're trying to make room for blood flow because you have a clogged artery. Cholesterol is in the way. So they put the little balloon into the small hole that the cholesterol has left for you. They fill the balloon up. It smashes all the ooey gooey yellow stuff to the edges of the artery, and now blood can flow better. Anyway, it's actually what's done. Now we're going to use mathematics. It says, suppose the balloon is inflated at a constant rate of 44 cubic millimeters per second. What that means is, after 0 seconds, there's 0 cubic millimeters. So after 1 second, there's 44. After 2 seconds, there's 88. After 3 seconds, there's 132. After 4 seconds, there's 156. After 5 seconds, there's 220. How am I getting those numbers? I'm just multiplying. What am I multiplying? 44 times the amount of seconds. Oh, you mean 44 times t. Because question A says, find a volume after t seconds. There it is. 44 times t. It's linear. It's just 44 is the slope. Every second, you've got 44 more than you had last second. Ta-da! Is it? You think? What do you want me to do? 26 times that? 26 times 44? 1,144. You said 1,044. That's not what I heard. You know what? I got it on tape. We'll roll the tape back and we'll see what it says. I'm kidding. They won't be able to hear you. Huh? You mean the people in the crowd? Yeah, that's because the microphone's stuck to me.
I mean, speak really loud.
Okay, buy them. You buy the mics. I'll have you mic'd up.
All right. Wait, I have one.
No, but it would have to connect to this tiny Bluetooth dongle right here.
There's only one space on that.
No. Hold on, I'm pausing the video. We're wasting video time. Hold on. It's fun. So we have to keep going. Part B. It says when the volume is V, what is the radius? So what part B wants you to do is part B wants you to take the volume of a sphere equation and solve for radius. In case you don't know the volume of a sphere, it's 4/3 pi r cubed. 4/3 pi r cubed. And that can actually be written as that. Because the pi is pi over 1, so it's over 3. But I specifically changed the equation to that because we know we're trying to get r by itself, right? So I'd like you to see that there are two things we need to deal with. One, there's a fraction next to our r, and two, there's an exponent on our r. That's hard to say. So what are we going to get rid of first? The fraction. How do we get rid of fractions? Ooh, good word, reciprocal, yes. We need to multiply both sides by the reciprocal. Fractions are our friends.
I didn't learn them right, so fractions are like with grammar in English. I don't get it.
Fractions are our friends.
I got better friends.
This fraction cancels that fraction. And what we're left with is r cubed equals, yes, I switched the order, but that's okay. On this side, I have 3v over 4 pi. Because this is technically v over 1. What? I wrote this on the right side, this on the left side. This from the right side here, that from the left side there. I just multiplied. 3 times v over 4 pi. Now I can get r by itself using the cube root. Which means the radius of this catheter is the cube root of triple the volume divided by 4 pi. Now, if you take a peekaboo at question C, what just happened was I took the volume of a sphere equation and I got r by itself because it said, what is r? So we just solve for r. And you might notice that my equation for r, its variable is v. This says write an equation that gives the radius in terms of time. And we can pull that off because this is what the volume equals. And I could plug it in to that. I could compose my volume function that I did in part A with my radius function that I did in part B to get that the radius is the cube root of 3 times 44t over 4 pi. Now this does clean up a little bit because 44 over 4 is 11. So it gets a little bit pretty. So you have 3 times this equals 11, so it's 33t over pi, like that. What question C asked us was, what is the radius at 5? No, I explained it. I did 44.
You explained it, but you didn't explain it in the paper. Are you not showing your work?
What are you talking about?
Ooh, what's the doctor?
How do you show that work?
Because you know how you showed like the thing that it's by 11. You're not doing it long. You're doing a lot of short.
You mean I didn't write 3 times 11?
Okay. It just sometimes when you're just glancing over, it takes you a little bit longer to like get it.
Here's what happened.
All the short.
Here's what happened. You guys tried to multiply 3 and 44 and then divide it by 4. That's inefficient. I would divide before I multiply. Yeah. So this equals 11 right here. This is 11. And 11 times 3 is 33.
I understand that. It's just that what we were saying about is that when you just glance at it, it takes you a second to look at it. That's
Okay, anyway. The question says, what's the radius after 5 seconds? I don't know what 33 times 5 divided by pi is, and I darn sure don't know what the cube root of that is. And that's why we're going to grab our technology. Okay. Press the math button, because the math button is where you find structures, math, and you will notice that the fourth option down is your cube root. The fifth option down is any root you want, fourth root, fifth root, sixth root, seventh root. But since we're doing cube root, and cube root's one of the shortcuts, I'll just hit the number 4. I need a stacked fraction, so alpha y equals n over d. And I'm just going to do 33 times 5 over, and I'm going to use the pi button, which is right there, second caret, and then I'll just hit equals. And since this is AP, we will round to 3 decimals, 3.745. And if that's what you write and stop right there, you miss one of the marks. What's missing? Units. There it is.